Okay, so what's the example here? The example is that we have a rod of length L. So let's say this is the rod of length L. And of course you have a charge, from here to here, which is of course a uniform charge distribution, and you have charge density lambda equal with Q over L, the length of the rod. And and what we're trying to find here, we're trying to find what is the potential in a point, let's say P in the y-axis, which is located at the distance A from the beginning of the road. So again, to state again once more, what is this problem about? So you have this road here that has a charge, which is, it has a continuous charge distribution. That's why the lambda, which is the charge density, is equal with Q over L, where L is the length of the road and Q of course is the total charge on the road. So the question is to find the potential at a point P on the y-axis, which is at distance A from the start of the road. So, as we said again, in all of these problems, you start from expressing the element of what you are looking to find. So in this case of P, so you have to express dP as a function of some other element, which in this case is the Q. It's the element actually dQ. So the element charge, and of course the formula is that dP is equal with K, which is a constant, times dQ over R. So that's the formula. So, and of course R, it's this distance here. So that's the first step, where you start from. So write again, dP is equal with K dQ over R. So now the second step is you have to you have to be able to write this part here in terms of a variable, which is the independent variable in the problem, and also the variable that you can calculate the limits. So that implies also that that's what will be the final physical quantity in which you will have to express the integral. So here, of course, since we have this formula here that lambda is equal with Q over L, from that you have that of course Q, we can replace this with lower Q, is not a problem. So you have that Q is equal with L, with lambda times L, and of course if you take the derivative of both sides of this equation, you will have that dQ is equal with lambda, because lambda stays constant, times dl. So that means that when you go and you substitute this here, you will have that k, this here becomes k, and instead of dq you put lambda dl over r. And now you see that this here is what we have to find the integral in respect with. So, and actually it's better to put, because, let's say this here is the quantity, this is the quantity that produces the dq. So, and actually, let's assume that this here has length dx. So that means that the dq it will be equal with lambda times dl, but because in this case, like we're working on the x-axis, we can replace this with equal with lambda times dx. So that means that we can have here x2 is not a problem. So that means that the variable that we have to express this integral here has to be the x, which is actually the the distance from the beginning of the road, or from the origin to the point that this dq is. So, and how we do that? You see that here you have r, but of course, because this here is a right triangle, if you take Pythagorean theorem, you have that r is equal with square root of a square plus x square, where of course x is this here. So, and if you go and you substitute this here, you will have that this will be equal with k lambda dx over, we said that r is equal with this here, so over a square plus x square. And of course, now we have to put the limits of this integral. So what are the limits of this integral? You see that x goes from this point here, which is the origin, so we can put here 0, so it goes from here to here. And of course, because we said that the length of the road is L, so that means that if this is the 0, here has to be the L, so that means that the limits of the integral is from 0 to L. And of course, here sometimes you might have that this and this is different, but actually the difference between them, it has to always be the same. So, because that's the only way that you will get the right answer, which of course it has to be always the same, independent of what will be the limits here. So, but always the difference between this and this has to be the same. So, that's the integral that we have to calculate. So, this integral here, we can take k and lambda outside since they are constant. So you have to calculate k lambda. So, and then you have to calculate the integral of dx with respect of x. Sorry, you have to calculate the integral with respect of x of 1 over a square plus x square, and of course from 0 to L. And this integral here is equal with so k lambda, and this integral here is equal with ln of x plus square root of x square plus a square So of course you have to integrate this from 0 to L. So that will give you, we can erase, it's okay, I think we can erase this, and we erase here, and we have enough space. So that's the integral, and you have to integrate this from 0 to L. So that means that you go and you put in the first whatever x L, so that should give you equal with k lambda ln of L plus square root of L square plus A square minus k lambda ln, and now you put whatever the lower limit of the integral. So it's you put whatever x0, so that should be 0 here and 0 here. So that means that it will be the square root of a square. So that should be the ln of a. So and this here finally you can write it as let's finish it here. Finally, you can write this here as we take KL as a common factor, so that should be K. So KL, K lambda, and then you have the ln of this minus the ln of this, which will be, of course, equal with the, because of the rules of logarithmic functions, you can write this ln minus this ln, you can write it as ln of L plus square root of L square plus A square over A. So, and that's the final answer to this problem. Yeah. So of course, here, of course, since dP, which is the element of potential, which is produced by the element of charge, so of course, that means that in order to find the P, you have to find the integral of this, so that's how this problem goes. And the final answer again is that the potential at this point P has to be equal with this here. So again, just to recap, we start from the fact that this element of this charge element dq produces this element of potential at this point here, and we continue with the substitution because this here is a continuous charge distribution, so that means that lambda is equal with q over L, so that's why we're able to substitute this with this. Then since x is the variable, the independent variable here, so that means that we express this, we have to express this integral in terms of x. So that means that the only thing we have to substitute here is the r, which is this here. From the Pythagorean theorem we can write it like this, and then it's just math. So you have to find this integral here, which of course from integral calculus of a single variable, this here is equal with this, and then you just have to apply the limits and you get your final answer. So thank you for taking the time to view this video, and I hope you find it useful. and bye for now.